Hey, Dr. Clark here, and in this preview video, we're going to be looking at section 2.2 separable equations. Let's take a look. So first, we need to talk about an initial value problem. That's what we're studying in this section. So a first order initial value problem is a differential equation of the form dy dt equals f of yt with initial condition y of t0 equals y0. So derivative equals right-hand side with an initial condition. That's a initial value problem. And we're looking at first order initial value problems here. So just one derivative. All right. And what we're going to do is upgrade that to say it's separable if one thing happens. So it has to be right-hand side separated into the product of all the t's and all the y's. So all the t's should be able to be factored out and gathered into one function, multiplied by all the y's, which are factored out and gathered into another function. So that's what it means to be separable. So we can separate them, and notice it's important that they're separable via multiplication. So t squared times y, there's your t's, there's your y's, they're separated. That would be separable. T squared plus y is not separable because you cannot write that as the product of things with t's and things with y's. It's actually the sum in this case. All right. Sometimes you have to do some algebra to factor out the t's or factor out the y's to get it in the right form. But if it's separable, you can separate into those two parts. Okay. Now notice any autonomous differential equation, you can just set g of t to be 1. If it's autonomous, there's no t's, so that's 1 times h of y. So autonomous is always separable. For example, the logistic equation dp dt equals kp 1 minus p over n. There's no t's, so g of t is 1. Everything else is in this case p's, so that's separable. All right, and what we're going to see is you can actually always solve a first order separable differential equation. What you do is you think of dy dt in terms of differentials, and so you multiply this dt up to the other side and divide h of y down to this side, so you get the t's on right hand side and the y's on left hand side. You do that via multiplication. And then you can basically think of this as a function dy and this is a function dt, which looks like an integral. So if you just put an integral on both sides, so you integrate both sides, notice you're integrating with respect to y on left-hand side, integrating with respect to t on right-hand side. What you'll get is a function of t and a function of y, and if you just solve for y as a function of t, you've got yourself the answer to the differential equation. When you do the integral, you get a plus c that comes out as the constant of integration. So that is, you expect to have some constant, although if it's an initial value problem, that c will end up being determined by the initial condition. So essentially you might say, well, hey, we can solve any separable differential equation. Well, if you took Calc 2, which you should have before taking this course, you'll know that not all integrals are very easy. So it's if you can do the integrals, that's great. You'll find y as a function of t. But there's lots of situations where the integrals are hard to do. So in theory, we can solve any separable differential equation, but that in theory is actually limited by our ability to do calculus. Okay, so what we should have seen here is just what is a separable differential equation. We can separate it via multiplication. And then how are we going to end up solving these? Well, we're going to separate the y's on one side, the t's on one side, and when we integrate both sides, you'll get t's and y's, and then solving for y will give you a solution to a differential equation. We'll see some examples in class where we actually do the calculus and get the answers, and what you're going to find out is a bunch of the examples of modeling that we've done already will show up as problems that we can now solve, so that'll be fun. All right, well, I'll see you in the next video, and I'll see you in class.